Well, simply put, any motion of charge from one place to another constitutes current. So, in the earlier chapter on electrostatics, we assumed the charges are stationary and do not move. Therefore, we can safely say that there is no current under this situation. But then, if you really zoom into the conducting material, what you will see is that the electrons are zipping around at very high speeds of the order of 10 to the power 6 meters per second. So, why do we say that this random motion of electrons is not current? Well, the answer is that the random motion of the electrons tends to prevent the net motion of these electrons in a particular direction, or in other words, collectively all the electrons just stay in the same volumetric space all the time. And if there is no forward motion of the charge, it cannot be called current. So in short, current can happen only if the charges move forward, even if the speed is very low. In fact, we'll see later in this chapter that the forward speed of electrons in the current that flows in the wires laid in our houses is actually very slow and of the order of 10 to the power minus 4 meters per second. So, how do we make these electrons move in forward direction to produce current? To do so, let us apply a potential difference between the ends of this wire and produce an electric field. Then what will happen is that any charged particle inside this wire will experience a force due to the field, which will make the negatively charged particles move opposite the direction of the field and the positively charged particles in the direction of the field. Well, for now we are talking about electrons, and therefore we can say that they will start moving in this direction, that is opposite the direction of the field, and the value of the force on each electron will be F is equal to E, capital E, where E is the charge on the electron and capital E is the value of the field here. Now, if this electron was in vacuum, we know that the force F would have accelerated the charge and it would have gathered speed, but this does not happen when the charge is in a conductor. That is, the electron does not speed up. The reason for this is quite simple. What happens is that as the electrons move forward, they constantly collide with impurities in the conductor and the ions of the material that are stationary, and these collisions randomly change the velocity of the electrons so that some electrons are going to the left and some to the right, some north, or some are going to the south. So what I'm trying to say is that the net velocity becomes zero, or look another way, the collisions are disallowing the electrons from gathering speed in forward direction. So what happens is that the random collision of the electrons combined with the force they experience due to the electric field makes them drift forward at a very slow pace, and this drift has a certain velocity and we call it the drift velocity of the electrons, and this collective forward motion of electrons is what we call current. Now, while the velocity of the electrons as they jet around is of the order of 10 to the power 6 meters per second, that is very high, the drift velocity you see here is often surprisingly small and of the magnitude of 10 to the power minus 4 meters per second. Okay, so let us now try to understand the idea of direction of flow of current. So when the electrons are moved by the electric field, the field does work on the electron. And we know that when work is done on an object, it gains kinetic energy. So here also the electrons gain kinetic energy, but most of the kinetic energy gained gets lost by the electrons to the ions of the conducting material due to multiple collisions the electrons have with the ions of the conducting material. So this kinetic energy lost by electrons to the ions ends up heating conducting material and raising its temperature. Well, you might think this as a waste of energy, but then it depends on the application of the electric current. That is, if you're using this current to heat up your toaster, these collisions actually result in heating up the element of your toaster. Any which way, this collision of electrons with the ions of the conducting material is something unavoidable when current is generated. What you would have observed is that in each diagram we have shown so far, the direction of movement of charge is that of electrons. So if you take this wire where we are applying an electric field in this direction, the electrons will tend to move in this direction. But strangely, and you must listen to this carefully, we say that the direction of current is this, and we call this the direction of the conventional current. So in essence, we say that the motion of the electrons in this direction is equivalent to motion of positive charges in this direction. There's something important to remember, and for all explanations and problems we encounter in future, we will follow this conventional current as the direction of the current. So if we take this circuit, we can clearly see that the electrons would move like this, but then we say that the direction of current is this. Strange due to historical reasons, but that is the way it is. Well, staying with this circuit, let us say the amount of charge that passes through a section of a wire, say this one, is dq, and time it takes for dq to pass through it is dt. Then we say that the current through the wire is I equal to dq upon dt. And in steady state, this would be the same for any cross section of the wire, or simply put, the entire length of the wire. So current is simply the rate at which charge moves through any cross-sectional area of the wire. You can also see the units of current are coulomb per second, or the more commonly used term you all know is ampere. So if someone told you that here in this section 9 coulombs are passing every second, you should be able to say that the current in the wire is 9 ampere. Well, to stretch the explanation a little more, we can say that since 1 coulomb is equal to 6.24 into 10 to the power 18 electrons, the number of electrons that have passed through in 1 second here is 9 into 6.24 into 10 to the power 18. That is 56.16 quintillion electrons have passed this section in 1 second. Now, let us find the magnitude of drift velocity of the current we spoke about earlier through some simple mathematical jugglery. So if we zoom into this wire, what we will see inside is that the direction of the electric field is this, and the current that are positive charges are also flowing in the same direction. So we are no more talking about electrons here, but the assumed positive charge moving in a direction opposite to the electrons. So this here is the conventional current. Now let us say that there are n charges per unit volume, which we call as the charge density, and the units would therefore be per meter cube, because you got to remember n is just a number. So you don't say coulomb per meter cube, it is just per meter cube. Further, we assume that all charges move at the same drift velocity, say Vd. Then if we take this as a section through which the charges are streaming, then in dt seconds, a charge here would have moved a distance Vd dt, and behind it several charges would have gone past this line. In a way, in time dt, this volume containing charges has moved past this section. Then volume of such a cylinder is distance Vd dt into the cross-sectional area A, that equals A Vd dt. And if n is the number of charges per unit volume, then this volume contains n A Vd dt charges in it. Now if we say that the charge value of each charge is E, then the value of dq, or the charge that passes by in time dt, is E into n A Vd dt. And therefore the current, according to the definition we agreed on, is I is equal to dq upon dt, which is equal to E n A Vd dt upon dt, which equals Ne Vd A. Now let us say we wanted to study the flow of current across a cross-sectional area at a particular point. To do so, we'll introduce a concept of current density at that point. That is, if we were to divide the value of current at that point by the area through which it flows, let us say here in this wire, what we get is a term called current density, and it is denoted by the symbol J, and it would equal Ne Vd A by A, that is Ne Vd. And the units of this are ampere per meter square, and this term here inside the brackets is often called the carrier charge density and has the units coulomb per meter cube. Well, we could also define a vector current density J that takes into account the direction of the drift velocity vector Vd, and in that case J can be written as vector J is equal to NQ where Vd is a vector. Now, one quick observation you might like to make is that current density is treated as a vector but not the current itself, and the reason is that vector J describes how the charge flows at a certain point, and the direction of the vector indicates the direction of the flow at that point. But current I is something that flows through an extended object like this wire, and it has the same value at all points across the circuit. But J does not, because it depends on the area of the cross section at a point where the current is passing. So you see J here is directed in the downward direction and here in the upward. Also, the current density can vary across the circuit depending on the area of the cross section. So you see this part of the circuit where the current is passing through the battery, the J value would be less considering the cross-sectional area of the battery is a lot more compared to the wire where the J value will be less. Well, to make it easier for us to understand this topic, we could draw an interesting comparison of flow of electricity with that of water flowing down a hill. So let us see how the flow of river changes as the conditions on the hill change. So here you have smooth flow of river from a higher elevation to lower elevation, or from a place of higher gravitational potential to that of lower gravitational potential. Quite the same way, electric current or the charges flow from a place of high electric potential to a place of low electric potential. So more the difference in elevation, faster the flow of water, and likewise more the difference in electric potential, more the flow of charges or current. Now, what if we had a lot of trees and rocks on the hill? Will the water flow as fast as it was earlier? No, it would not, because the water will keep bumping against the trees and rocks that will slow down its flow. So you see, the flow of water is determined not only by the difference in potential, but also what is present in its path of flow. Well, for electric current also, the flow of charges is determined not only by the potential difference, but by a property that is called the resistance of the wire that can slow down the motion of charges that form the current. So with this simple analogy at the back of our mind, and you got to remember this is just an analogy and do not stretch the comparison too far. So if we were to apply the same potential difference between ends of two wires made of different material but having the same length and area of cross section, we will get different current values passing through each wire, and the difference in these values is because of the characteristics of material of each wire. One wire causes more resistance to the movement of the charge carriers than the other, causing a lower value of current for a given potential difference. And It's actually quite easy to find the resistance of each wire. All we need to do is measure the current flowing through the wire when a potential difference V is applied across the ends. And let us say this current value is I. Then we can say that the resistance of the wire is R is equal to V upon I. And you can see that this has units of volt per ampere, and we call it ohm using this as a symbol, or we could say 1 ohm is equal to 1 volt per ampere. And a piece of conductor that may be used in a circuit to provide a specific resistance is called a resistor and shown by a symbol like this. Okay, now let us rewrite this equation as I is equal to V upon R. Then we can say that for a certain applied potential difference V, more current will flow if the resistance is low and less current will flow if resistance is high. Well, this seems quite natural. That is, the charge flow will be faster if there is less resistance, and if charge flow is high, current would be high as well. But then what was found was that the resistance of a wire also changes if you increase the length of the wire. So longer the length, more the struggle for the charges to move through it and more the resistance. Further, it was found that the cross-sectional area of the wire also has a role to play in determining the value of resistance. A larger cross-sectional area would help the charges to move a lot easier compared to an area that is small and say constricted. Hence, large cross-sectional area means lower resistance. So to sum up, what we can say is that if you are given a wire made of certain material, then the wire will have different resistance depending on its length and the area of cross-section. So let us try to find a quantity that would be fixed for a material irrespective of its geometric shape. Well, based on what we have discussed so far, we can write that resistance of a material is directly proportional to length and inversely proportional to the cross-sectional area of the wire. Then if we think about what material is the wire made of, we can introduce a constant called resistivity that represents the characteristic of the material of the wire. Resistivity is what allows or say disallows free movement of charge through the wire. We could compare the situation with water flowing in a pipe, and if the pipe is totally clean, the flow of water would be fast. But if there are pebbles, stones, and say pieces of cotton stuffed inside, the flow would become slow. Likewise, the material of the wire could have impurities and ions of the material itself that slow down the movement of the charges. So we say higher the resistivity of a material, more the resistance. And so finally, we define resistance of a wire as R is equal to rho L by A. Now here you can see resistivity is characteristic of a material and remains the same for any size and shape of a given material, but resistance of course changes with shape and size of the wire. More formally, we could define resistivity of a material as electrical resistance of a conductor of unit cross-sectional area and unit length, because if you put unit value for L and A, what you get is the resistance value for that dimension. So resistivity, you see, is property of the material, much like say density, that is having 90 grams of water in a cylinder or 300 grams of it in a cube does not change its density. In either case, density of water, that is mass per unit volume, remains the same at 1 gram per cubic centimeter. So rho is a fundamental property of the material like density, melting point, etc. Well, we just derived the relationship between resistance, length, area and resistivity in a slightly intuitive way. Let us try to do the same derivation taking a different approach, which I'd say is also quite simple. So we defined resistance R of a resistor as equal to V upon I. But what if we were to focus on a point on this resistor? Then rather than using potential difference across the resistor, we use electric field E at that point. So instead of saying that the potential difference V is driving the flow of charge between these 2 points, now we are saying electric field E is pushing the charge at this point. Then in the denominator, we can take current density J at this point rather than the entire current through the resistor. In that case, what we get is resistivity rho on the left hand side instead of resistance. And considering resistivity is a material property and a constant, we can say higher the resistivity of a material, higher the electric field required to create charge density J. Or in simpler words, more electric force is required to move charges at a point because the resistivity of the material does not allow easy movement of charges. So theoretically, you could say that if you have a perfect conductor, its resistivity should be 0, and if it is a perfect insulator, its resistivity should be infinite. So metals, you could say, are good conductors and are more towards the left hand side and therefore widely used in wires used for conducting current. On the other hand, insulators like ceramics and plastics will fall on the right hand side of this line. Now let us break down this equation further and say the length of the wire is L and the area of cross section is A, and if we assume current density to be uniform across the wire, we can write E is equal to V upon L and J is equal to I upon A. Then if we put these in this equation, what we get is rho is equal to V upon L by I upon A. That equals VA upon IL. But we know that V upon I is resistance of the wire. Then what we get is rho is equal to RA upon L, or R is equal to rho L upon A. Let us also make a quick assessment of how resistivity of a material changes with temperature, because we know that most fundamental properties change with temperature and resistivity is quite the same that way. So what has been found empirically, that is as a result of several experiments, is that the relationship of resistivity with temperature is linear for several metals and can be written as rho minus rho naught is equal to rho naught alpha into T minus T naught. Here T naught is the reference temperature, often taken as 293 Kelvin, and rho naught is the corresponding resistivity at 293 Kelvin, and alpha here is the temperature coefficient of resistivity, and the value is taken in such a way that the equation gives good agreement with experiment for temperatures in the chosen range. So for most problems, you'll have these values available for you to solve. Now, while resistivity is a material characteristic that determines resistance to current flow, the reciprocal of this value represents the conductivity of the material or its ability to let the charge flow, and conductivity of a material is shown by the symbol sigma. So we can say larger the resistivity of a material, lower the conductivity, and lower the resistivity, higher the conductivity. As an example, we could take copper that has a resistivity of 1.68 into 10 to the power minus 8 ohm meter, which is very, very low. And if you take its reciprocal, what you get is 5.96 into 10 to the power 7. That is very, very high, essentially indicating that it has very high conductivity, and that is precisely the reason why copper is used in making electric wires, because it helps easy movement of electrons and therefore the current through the length of the wire. Hello and welcome back to a lesson that covers two very important concepts in electricity, and these are the Ohm's law and power. We will cover what really is Ohm's law, what is power, and in the end we'll solve a problem to get better clarity of the topic. So in the previous lesson we learned that a resistor is nothing but a conductor with certain resistance, and this resistance does not change even if you change the applied voltage or the direction of the current by switching the wire connections at the terminals of the battery. Well, let's take this a little further and find what Ohm's law says about this. So let us take this resistor and find how current I changes as we vary voltage V, and we'll plot these values on an I versus V graph. Now to start with, we'll apply 0 volts across the terminal, and no surprise, we get 0 current. Then we increase the voltage to 1 volt and we find that the current value is 2 milliampere. Then we increase the voltage to 2 volts and we find the current in the circuit is now 4 milliampere. And when we crank up the voltage further to 3 volts, we see that the reading on the ammeter as 6 milliamperes and so on. So if we connect these points, what we see is that we get a straight line plot between the applied voltage and the current that flows through the resistor. Now let us reverse the connections at the terminal of the battery so that the current flows in the other direction. So now we indicate the current value with a negative sign since it is flowing in the opposite direction, and we do the same to the voltage by putting a negative sign since we have reversed the attachment at the terminal, or more technically we say we have reversed the polarity. Then when we repeat this exercise of increasing voltage and measuring current, we again find the same absolute values, and therefore we get a line like this in the reverse direction. So what we see is that the I versus V is a straight line plot passing through the origin, and the slope of the line is I by V, or 1 by R, that is a constant for all V values. So if I by V is a constant, V by I will also be a constant, and since V by I is nothing but resistance R, we say that the resistance R has not changed with changing voltage, or R is independent of the applied potential difference, and we say that such conductors follow Ohm's law. On the other hand, we could have conductors where if we change the applied voltage, we can end up getting a graph like this, and we can clearly see the applied voltage and the current does not have a linear relationship, or the ratio V by I keeps changing with the applied voltage, and since V by I is the value of resistance, we say the resistance is also changing with the applied voltage, and we conclude that such conductors do not follow Ohm's law. So to wrap up this topic, we can say that for conductors that follow Ohm's law states that the current I through such conductors is directly proportional to the potential difference V applied to the conductor. Well, another way of stating the same law is that a device obeys Ohm's law if the resistance of the device does not change with the magnitude of applied potential difference V. So most materials that are homogeneous like copper, silver or gold follow Ohm's law as long as the applied potential difference or the electric field is not too high. If the applied potential difference is very high, there would be a departure from the linear relationship that Ohm's law states in almost all cases. So this brings us to the second part of this lesson that deals with the application of current in our daily lives, and that is power. So what we have here is a simple electric circuit that has a battery and a conducting device. This could be a resistor, a motor, or any electrical device, and this battery here maintains a potential difference V across its terminals as well as across the ends of the device. And we know, looking at the setup, that terminal X is at a higher potential than Y, and as a result we get a steady current in the circuit powered by the battery that starts moving the charges as soon as the circuit is closed. So if we say that charge dq moves between terminals X and Y in time dt, then since current is nothing but the rate at which charge moves, current I should equal dq upon dt, or dq should equal I times dt. Then we can say that charge dq has moved from a place of high potential to a place of low potential, and this drop in potential is V. And if there is a drop in potential, the electric potential energy of this charge should also reduce, and this reduction in energy is denoted by du. That equals dq times V, which in turn can be written as I dt V. But then if this charge dq has suffered a fall in energy, this energy should show up somewhere per the law of conservation of energy. Well, this lost potential energy shows up as energy in the attached device. This energy could either heat up your toaster that may contain a resistor, or rotate the shaft of a motor to lift a heavy load, or even provide the chemical energy to a discharge cell. So what we say is that we are providing power to the attached device, and mathematically power is defined as the rate of transfer of energy, or P is equal to du upon dt. And if we use this equation, this equals I times V. And you can see the units of power here are volt ampere, and we can write 1 volt ampere equals 1 joule per coulomb into 1 coulomb per second, which equals 1 joule per second, and we write joule per second as watt. Well, a question that might come to your mind is that what really is happening at a microscopic level when power is getting transferred to the device? So what happens is that as the electrons move at a constant drift velocity between the terminals, their kinetic energy remains the same, but the potential energy reduces, which, as I explained earlier, shows up as transferred energy to the attached device, and this transfer is on account of collision of electrons with the molecules of the resistor, thereby increasing temperature of the resistor lattice. So you see, the mechanical energy of the electron is converted into thermal energy that is gained by the resistor, and this process cannot be reversed. Now we can further break down this equation into more useful forms by assuming the device has resistance R. Then if we combine this equation with this, what we get is P is equal to I square R, or we could also write it as P is equal to V square by R. Now here I would like to point out that while this formula is applicable to any kind of energy transfer to an electrical device, this one you see that we just derived can be used only when the device attached has resistance. So let us try to work around a problem on power to get a full grip on the concept. And what we have here is a heating coil that we use at home, and it has a resistance of 100 ohms. The question is, at what rate is heat generated if a potential difference of 150 volt is applied? Well, this is a simple one. We use the formula P is equal to V square by R and calculate power generated as 150 square by 100, that equals 225 watt. Now comes a tricky question. So what if we divide this wire into two equal parts? Then what power can be generated from each if we subject them to the same voltage of 150 volts? Well, does not seem difficult. We know that resistance of a wire is directly proportional to the length of the wire. So cutting it into two, makes the resistance of each wire 100 by 2 or 50 ohms, then the power generated in first coil is 150 square by 50, that equals 450 watt, and the same in coil 2, or a total of 900 watt. So this means we are getting 4 times the power by just cutting the same wire into 2 parts, which anybody would think is great. But then why is it not a smart thing to do? Would the current consumption remain the same or change? Think about it and see if you can find the answer. If you do, share the answer in the comments below and we can have an interesting discussion. In this lesson, we will understand what exactly is electromotive force or the EMF and how it helps us to generate current. So let us put a capacitor in a circuit, and when we do so, what we see is charge flowing from the positively charged plate to the negatively charged plate. But then as the positive charge flows from this plate to this, it neutralizes the negative plate, and then the flow of the charge stops as both plates reach the same potential or become neutral. So you see the current did flow, but for a short while. But to get real flow of current in a circuit, we need to figure out a way of pumping the charges continuously. And this can happen only if we can find a device that can do so, and we put that in the circuit. Well, such devices are called EMF devices, and one such EMF device is a battery. So a battery provides a force to the charge carriers to enable them to keep moving in the circuit and therefore generate current. And this force comes from the chemical energy of the battery. So let's see what really happens when we introduce such a device in a circuit. Well, to explain the idea, I would first like you to imagine yourself to be in a ski resort where you are at the top of a hill. And since you have the gravitational potential energy, you can slide down the hill, but while doing so, you lose the potential energy when you reach the bottom of the hill. Then, if you wish to continue skiing, you have to be carried up to the top of the hill by some external force. Well, this could be a lift that takes you up to the top of the hill against the force of gravity and therefore does work in carrying you up. Then once you are on the top of the hill, you again have the gravitational potential energy to slide down. Now let us use this analogy to explain what is happening here inside the battery. So a charge at this point where the potential is VA can move through the circuit because it is at a high potential, quite like when you are at the top of the hill and slide down. It moves through the circuit and reaches a point of lower potential VB. Now this charge cannot automatically move from this place of lower potential to a place of higher potential on its own, and you can see the reason is that the direction of the electric field is downwards from the positive plate to the negative plate, and therefore a positive charge has no chance of moving towards a positive terminal against this field. Quite like you cannot move to the top of the hill on your own against the force of gravity. So eventually what will happen is that all the positive charge would move from point A to point B and neutralize the negative charge, and therefore the original potential difference VAB that existed will become zero and both points would come to the same potential. So what can we do if we want the current to continue flowing? Well, we need a force that will take this positive charge from this point to this and in the process raise the potential of the charge, quite like the force of the lift that overcomes the gravitational force to take you to the top of the hill. And this force here is provided by the chemical force of the battery. So let us go ahead and denote this force as Fn. So you see this force Fn is carrying the positive charge from here to here, thus creating a positive potential here and a negative here. In a way, the force is helping maintain the potential difference VA minus VB that would have otherwise become 0. So you see, Fn, that is a non-electrostatic force, just about overcomes the electric force Fe and carries the charge up to the positive terminal. And so we say Fn is equal to Fe. Now, since force Fn causes displacement in the same direction as itself, we can say positive work is done, but then we also see that force Fe is acting on the same charge in a direction opposite to the displacement and hence does negative work. So the total work done is 0, and if the net work done is 0, the kinetic energy of the charge does not increase. But you can see the potential energy has increased since it has moved from a place of low potential to a place of high potential. It is quite like you moving from a place of low gravitational potential to a place of higher potential without changing your kinetic energy, but still increasing your potential energy. So this source of non-electrostatic force continuously maintains this potential difference VA minus VB between the terminals to allow the charge to keep moving around in the circuit and therefore helps generate the current. Now, let us understand the same thing through a few simple formulas. Well, we say that the work done by the chemical force of the cell in moving a unit charge from B to A is denoted by this symbol, or kind of a curly E is what it looks like. It therefore has units of joules per coulomb or volt, in a way quite like potential, and this symbol is often called the electromotive force. But it is not really a force as we just saw, but traditionally it has been termed that way. So when we say that a battery has an EMF of 1.5 volts, what we mean is that the battery does 1.5 joules of work to move a unit charge inside the battery from one terminal to the other, or more accurately from a place of lower potential to higher potential. So if we moved a positive charge Q from terminal B to A, the work done by this chemical force would therefore be Wn is equal to Q times the electromotive force. Now, since the potential difference between point A and B is VA minus VB, or let's call it VAB, the potential of the charge Q goes up by Q times VAB. And since we just showed earlier that there is no change in kinetic energy of the charge, the work done on the charge by the non-electrostatic force must equal the change in potential, or Q times the electromotive force is equal to Q times VAB, or the electromotive force is equal to VAB. Now, let us put this battery in an actual circuit where there is a resistance R. We know that the potential difference between the terminals A and B will create an electric field in the wire that will make current flow from A to B. Let us say the value of this current is I, then the potential difference between the ends of the resistor can be given as VAB is equal to IR. Then if we combine this equation with this, what we get is electromotive force is equal to VAB is equal to IR. Well, we could interpret this equation as the rise in potential of a unit charge as the charge moves from B to A is equal to the potential drop VAB across a resistor as the same charge moves through the wire from A to B. Now, we say that this is an ideal source of EMF because there is no drop in potential inside the source. But then, just like there is no frictionless plane, in reality, every source of EMF, in this case a battery, also has an internal resistance that causes a drop in potential. And if this resistance is denoted by a symbol R, then as current I moves through this resistance, the drop in potential would be I times R. So we can say that VAB is equal to electromotive force minus IR. So this is called the terminal voltage with internal resistance. Look at it another way, the increase in potential energy of unit charge VAB as a charge moves from B to A inside the source is now less than the work done by the electromotive force, since some potential energy is lost in overcoming the internal resistance. So if you are given a battery that reads an EMF of 1.5 volts, you can say that the terminal voltage VAB will also be 1.5 volts as long as there is no current flowing through it. That is, I is equal to 0. But the moment current starts flowing, the terminal voltage reduces by an amount IR, where R is the internal resistance of the battery. Now, let me close this lesson by summarizing the key points, since this topic is a little tricky and needs a bit of repeat watching to understand better. So point number 1 is that an EMF device like battery does work to maintain potential difference between its output terminals. 2, an ideal EMF device is one that has no internal resistance, in which case the EMF equals the terminal potential difference. 3, in reality, every EMF device has internal resistance that causes reduction in terminal voltage. And 4, the terminal voltage will be the same as the EMF if there is no current or I is 0. So here is a circuit that has a battery with an EMF E, a resistor R, and the wires that connect the two. And going forward, we'll keep in mind that the wires themselves have negligible resistance unless the problem mentions that the wires have some resistance. So wires in a way are like channels through which charge carriers move. Now let us pick some point on this circuit. Any point, let us say this one here, and start moving in one of the directions, that is clockwise or anti-clockwise. And while we do so, we'll algebraically add the potential drop or gain as we move along the path, so that when we return to the same point again, the net gain in potential would be 0. Now, this point which I just made needs to be understood very clearly. And to do so, I would want you to imagine that you are on a mountain and you trek around on it, but finally get back to the same point from where you started. Now, the question is, would you have gained or lost height relative to the ground level? Well, it is obvious that if you get back to the same point from where you started, you would not have gained or lost any height because you are at the same point from where you started. So let us see this by adding any gain in height as we move and subtracting as we lose any height relative to the ground as we move from start point and get back to the same point. So let us say you start from a point that is 100 meters above the ground and reach this point that is 10 meters higher. So you add 10 meters to your original height. Then you come down by 25 meters. So we subtract 25 meters and then you decide to go down by another 5 meters. So we further subtract 5 meters and then you finally decide to go back to your starting point and therefore move up 20 meters. So we add 20 meters. Then if we add up this rise and fall to your original elevation, what you'll find is that the final elevation is the same as the starting point elevation, and so this equals 100 meters, which should be the case. Well, if we apply the same idea in circuits where we say that if you start at a point and come back to the same point, your final potential should be the same no matter what you encountered on the way. Or in other words, the net gain and loss in potential on the way should be 0. In fact, this is what is called Kirchhoff's loop rule or Kirchhoff's voltage law, and in a more formal way, it states that the algebraic sum of the changes in potential as we move in a loop of a circuit should be 0. So let us apply the same principle to this simple circuit and see if it works for us. We'll take A as the start and assume the potential here is VA, quite like the initial height at which you started your mountain trek, and move in a clockwise direction till we are back at A, and while we do so, at each step we'll know the gain or loss of potential. Again, quite like the gain or loss in height during your trek. So let us start moving, and as the charge moves from here to here, what we see is that we have moved from the lower potential point of the battery to the higher potential, and so the charge has gained potential, and we know the potential difference is E, and since there is a gain, we will label it positive. So let us move on, and as we move along this wire, there is no change in potential since the wire has negligible resistance, or in other words, no effort is required or no work needs to be done in moving the charge between any 2 points of the wire itself. So let us keep moving, and we cross resistor R. Here the charge moves from a place of higher potential to lower potential, and the drop is given as V is equal to I times R, and since it is a drop, we take this as a negative number. We keep moving in clockwise direction along this lower length of the wire, and again, since the wire has no resistance, there is no potential drop, and we once again reach point A from where we started, and the potential here is VA. So the way we found ourselves at the same elevation on the mountain when we reach the starting point, this should equal VA. Then what we find is I is equal to E upon R. Now, what if we had decided to move in a counterclockwise direction? Would we have got the same value of I? Well, let us find that by using loop method again. So now we move from point A to the bottom of the resistor, but this time we find the potential increases as we move to the other end of the resistor, because you can see the current will always move from a place of high potential to a place of low potential. So if current is moving down in this direction, this place must be at a lower potential than this, and therefore there is a gain in potential when we move across from here to here, and we therefore take a positive sign. Now we keep moving and reach the positive terminal of the battery, and then onto the negative terminal, which is clearly a drop in potential of magnitude E, and therefore we take a negative sign, and again we find that I is equal to E upon R. So you see, loop method can be used taking any direction around the loop, clockwise or anti-clockwise. So now, since you have some conceptual clarity around loop law or loop rule, let us try to memorize two important rules that will help us work with circuits that have more loops. So the first one is called the resistance rule, that says that if you are moving through a resistance in the direction of the current, the change in potential is minus IR. But if you're moving in the opposite direction, it'll be plus IR. And this is exactly what we did earlier. The second rule is if you are moving from the negative terminal of a battery to the positive, that is also the direction of EMF, the change in potential is positive. And this actually is quite obvious, since moving from negative to positive obviously means a gain or a positive E. On the other hand, if you're moving from positive to negative terminal of the battery or against the direction of the EMF, the potential will drop, and therefore we take minus E. Well, if you've understood what we've discussed so far, with some practice problems, you can pretty much become really good at solving problems around electric circuits. If you have not, I would suggest you continue watching the video and re-watch it, which will bring a lot of clarity after you've watched the second time. Okay, let us now study the same problem in another way, and this time around we'll also consider the internal resistance of the battery. So what we have here is a battery with an EMF E and internal resistance R, and like before, it is connected with a wire to a resistor R. So you see the internal resistance of the battery has been put inside this box to indicate that it is part of the battery. But at the same time, you can observe that the internal resistance can be shown like any other resistance in the circuit and treated accordingly. So this time what we'll do is stretch the circuit into a straight line as if it has been cut at this point and laid out straight. So let us say point A is at potential VA, then as we move to the right past the battery, there is a gain in potential since we're moving from negative to the positive terminal of the battery. Then it stays the same but drops by IR as the charge passes through the internal resistance R. It continues to be the same and drops again, this time by I times capital R when the charge passes through resistor R. And you see the charge is again at the same potential VA as it reaches back point A. So if we solve this equation for I, what we get is I is equal to EMF upon R plus small r. And you can see in this equation that if the internal resistance was 0, this equation would have reduced to the earlier derived equation of I is equal to EMF upon capital R. Okay, let us move ahead and consider a bunch of resistors in series connected to a battery with EMF E. Well, when we say resistors are in series, it basically means that we have connected or wired the resistors one after the other and the potential differences applied to the ends of the series. So you see here we have connected the three resistors between the ends A and B, and a potential difference is then maintained between A and B with the help of a battery. Now one thing you must note is that current across all resistors connected in series remains the same, and it is simply because you can see that whatever charge enters this side has to come out this side and enter the second resistor and then onto the third resistor. So as such, there is no loss of charge and therefore current remains the same across all resistors in series. However, as the charge moves through each resistor, its potential drops such that the total drop equals V. So if V1 is the drop in potential across R1, V2 across R2 and V3 across R3, then V is equal to V1 plus V2 plus V3. Now, what if we are asked to find value of a single resistor equivalent to these three resistors such that the potential difference across it is V and current is I? Well, we can find the equivalent resistance R by using the loop rule to both the circuits. So in this loop, we see that if VA is the potential here, then the equation we get if we move clockwise is VA plus E minus IR1 minus IR2 minus IR3 is equal to VA, or I is equal to E upon R1 plus R2 plus R3. And for this loop again, moving clockwise, VA plus E minus IR is equal to VA, or I is equal to E upon R. Then if we equate the two I values, what we get is E upon R is equal to E upon R1 plus R2 plus R3, or 1 upon R is equal to 1 upon R1 plus R2 plus R3, or R is equal to R1 plus R2 plus R3. And we can apply the same logic to n resistors if they are placed in series as well, such that R is equal to R1 plus R2 plus R3 plus so on and so forth till you reach the last resistor or the nth resistor. Often when you attempt problems around circuits, you are asked to find the potential difference between 2 points. So in this lesson, let us learn exactly that, and we'll do so by taking a simple circuit and establishing the potential difference between any two randomly chosen points. So here is a circuit that has a battery with EMF E, internal resistance R, and an external resistance of value capital R. and we are asked to find the potential difference between points A and B, or say VB minus VA, where VB represents a potential at point B and VA at point A. Well, what we'll do here is not very different from what we learned in the earlier lesson. So we start at A, where the potential is VA, and as we move up towards B, we will add up all the gains and losses in potential. So we first encounter the battery, and we can see there is a gain in potential. So we add the value of EMF to VA. Then we pass through the internal resistance of the battery, and since we are moving in the direction of the current, the potential should drop as we pass a resistor and move to the other side. So the drop in potential is IR, and then we reach point B, where the potential is VB. And if we've added the gains and losses to VA, this value should now equal VB. Then we get potential difference between A and B as VB minus VA is equal to EMF minus I small r. Well, we can also find the value of I, which equals EMF E divided by capital R plus small r. And if we substitute the value of I in this equation, what we get is VB minus VA is equal to EMF minus EMF R upon capital R plus R, which equals EMF capital R upon R plus R, that is capital R plus R. So you see, to find the potential difference between any 2 points, start at one point and move in the circuit towards the other point and add all changes in potential algebraically. This would be the potential difference between the 2 points then. Okay, let us shift gears and get an understanding of power that a battery of EMF E can generate. So when a battery establishes current by doing work on a charge carrier, what is happening is that the chemical energy of the battery is getting transferred to the charge that enables it to move in the circuit and create current. And since any EMF device, like a battery here, would have an internal resistance, some energy would get wasted there. So let us see how power, current, and EMF of a battery relate through a simple equation. Well, we know that the power a battery can generate is I times V, where V is the terminal potential difference and I is the current in the circuit. And we also know that the terminal potential difference is EMF value less the potential drop across the internal resistance of the battery. So if we substitute the value of V in this equation, what we get is P is equal to I times EMF minus IR, which equals I times the EMF minus I square R, that is small r. Now we can see that this term is the rate of thermal energy dissipation in the internal resistance R, or if we term this energy dissipation as PR, it equals I square R. In that case, this part of the equation, or rather this expression, must be the total rate of energy transfer by the battery, and let us call it PEMF. So PEMF is value of energy transferred both to charge carrier and the internal resistance of the battery. So let us now attempt a problem that will help us understand the concepts a lot better. And what we have here is a circuit that has two batteries with internal resistance R1 and R2 respectively, and there is an external resistance capital R as well. And the first question is, what is current I in this circuit? So to find the answer, let us label the direction of I this way, since we can see that EMF of this battery is more than that of this one, and therefore this battery will control the direction of the current. But even if you for some reason did not know the EMF values, you could have assumed some direction and proceeded. Let us now go ahead and apply the loop rule, and we'll move counterclockwise this time, that is against the direction of the current, starting at point A. And remember, you can start from any point. A is a randomly chosen point. So what we get is minus E1 here, since the potential drops, then plus IR1 since we're moving against the direction of the current, so there must be a gain in potential plus I capital R plus IR2 and finally plus E2, since there is a gain potential, and this should equal 0. Well, if you're curious, you could try establishing the same equation going in the other direction and using a different starting point. But I suggest you do it after you've watched this example. So if you solve for I in this equation, what you get is this as the expression for I, and if you put the values in the equation, you find the value of I is 0.24 amperes or 240 milliamperes. So the next question is, what is the potential difference between the terminals of battery 1? And this in a way is equivalent of asking what is the potential difference between points A and B, because you can see that A is at the same potential as this battery plate and B is at the same potential as this plate. Then what we can do is start at point B, that is effectively the negative terminal of the battery, and say the potential here is VB, and add the drops and gains till we reach point A, where we say the potential is VA, and we do so moving in clockwise direction. So what is important for you to note is that we do not wish to find VA or VB, but the difference between VA and VB, that would also be the terminal potential difference for battery 1. So the equation we have, if we go around the loop, is VB minus IR1 plus E1 is equal to VA, or VA minus VB is equal to minus IR1 plus E1. And if you put the respective values, what we get is VA minus VB is equal to 3.8 volts. Now you see this is lower than the EMF of the battery, and the reason for it is that the internal resistance of the battery has caused a drop in the potential when current I passed through it. And if there was no internal resistance, the terminal potential difference would have been the same as the EMF, that is 4.4 volts. In this lesson, we will learn how to work around multi-loop circuits. So what we have here is a circuit that has two loops. In fact, if you see closely, there are three loops. This, and this big one, and we have three resistors and battery as well. And for convenience, let us assume there is no internal resistance in the batteries. So let us pose a question to ourselves and ask, what is the current in the three branches we see here? Well, let us put some labels to current values to each branch and say that this one has current I1 flowing through it, this one has I2, and this one I3. And at this point of time, we will not worry about what really is the direction of the current. We have just assumed these as the directions, and you'll understand later that it's quite okay to approach multi-loop problems this way, that is, assign any direction to current if we do not know. So the direction of the currents have been taken arbitrarily. Now let us focus our attention on junction D, and we see that this junction is being fed with charges coming in due to current I1 and current I3, and the outgoing current is I2. Now since the charge in the circuit remains the same, we have to assume that the charge flowing in must be equal to charge flowing out. So we can say that I1 plus I3 should equal I2. Well, this is nothing but Kirchhoff's junction rule, or Kirchhoff's current law, very often written as KCL, and it states that if you add up all currents entering a junction, then it should equal the sum of currents leaving the junction. It is quite a simple rule that tells us that the charge is conserved if there is a steady flow of charge. In other words, charge does not build up at this junction or is lost. It is quite like water entering one pipe has to get distributed in two outgoing pipes. So if 3 liters per minute is entering through this pipe, then the outgoing pipes cannot give you more than 3 liters, or you cannot get 4 liters per minute. So you see, we have two nice tools for solving circuit problems. One is the loop rule that we learned in the earlier lesson, and the other is the junction rule. So getting back to our problem, we see that this equation has three unknowns, and therefore we need two more equations to find the current values here. So what we can do is use the loop rule for two different loops to get two more equations. Well, we can choose any two loops from the three that are available here. So let us pick this one and this one, and we'll first move around this loop in anti-clockwise direction starting at point B, and what we get is E1 minus I1 R1 plus I3 R3 is equal to 0. Then looping around in the second one in counterclockwise direction starting at point B, the equation we get is minus I3 R3 minus I2 R2 minus E2 is equal to 0. So you see, now you have three clean equations with three unknowns, and you can solve them to get values of I1, I2 and I3. Well, you could have also applied the loop rule to the big loop, and the equation you would have got moving in counterclockwise direction starting at B is E1 minus I1 R1 minus I2 R2 minus E2 is equal to 0. But you see, this is not of any use. This equation is of little use since we already have our three equations, and this one is anyway the sum of these two equations. Okay, with this in the background, let us work around resistors in parallel and how potential difference and current values show up in resistors when they are connected in parallel. So what we have here are three resistors that are set up in parallel to a battery with EMF E, and we assume that the internal resistance of the battery is 0. Now, when we say that resistors are connected in parallel, what we mean is, and hear it carefully, what we mean is that one end of each wire is connected together to one side and the other ends are connected together on the other side. And then the potential difference V is applied across the ends. So you see, each resistor ends up having the same potential difference V across, but different current values. So as a rule, when you connect resistors in parallel, each resistor has the same potential difference V that is applied across the ends. And if you want to remember the fact that resistors in parallel have the same voltage across, you can remember the word par V that essentially indicates resistors in parallel have same voltage. So here you can see that the potential difference V is given by this battery. Now, what if we are asked to find an equivalent resistor, Req, let's call it Req, that can substitute these three resistors such that it has the same potential difference V across it and has current I flowing through it. So to find Req, the first thing to do is find the current flowing through each resistor, and we can say that I1 is equal to V upon R1, I2 is equal to V upon R2, and I3 is equal to V upon R3. And if we go ahead and make use of junction rule, here what we get is I is equal to I1 plus I2 plus I3, which equals V upon R1 plus V upon R2 plus V upon R3, or we take V out and this is what we get. But we can also say for this circuit that I is equal to V upon R equivalent. Then if we equate the two I values, what we get is 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. And we can use this result to n number of resistors connected in parallel to get the value of equivalent resistance as 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on till you reach the nth resistor, for which you'll write 1 upon Rn. And an important observation here is that the value of equivalent resistance is always smaller than the smallest resistor that appears in the combination. Also, another thing you might wish to note and will be useful when you attempt problems is that since VAB is equal to I1 R1 is equal to I2 R2, means I1 upon I2 is equal to R2 upon R1, And this equation shows that the current carried by each resistor is inversely proportional to its resistance, or more the resistance, less the current that flows through it. In other words, current would take the path of least resistance. Okay, let us now attempt a problem to get a better understanding of what we have learned in this lesson. So what we have here is a multi-loop circuit that has an ideal battery and a bunch of resistors with these values. Then the first question is, what is the value of current through the battery? So let us see how we should approach this problem. Well, we could have started off by labeling current values in each wire as, say, I1, I2 and I3, and also noting that current I1 will flow through R4 as well, since I1 splits into I2 and I3, and when I2 and I3 merge again at this junction, you should get back the same current I1 here as well. After this, we could have then used the left loop to solve the problem, and the equation we would have got is E minus I1 R1 minus I2 R2 minus I1 R4 is equal to 0. But then you can see this equation has two unknowns, and we will need one more equation to solve the problem. So we may take the right loop to generate one more equation, but you might pause to realize that there is an easier way to solve this problem. So you can see that resistor R2 and R3 are in parallel, and we should find an equivalent resistance and replace them to simplify the circuit. So R23, or the equivalent resistance, is equal to R2 R3 upon R2 plus R3, that equals 12 ohms. So the circuit with equivalent resistance will now look like this, and we can see that current I1 that we labeled here will also flow through R23, since the two are now in series. So if we apply the loop rule here and move clockwise starting at point A, the equation we get is E minus I1 R1 minus I R23 minus I1 R4 is equal to 0, and plugging in the values, we get I1 is equal to 0.3 ampere. Now the next question is, what is the value of I2 through R2? Let us work backward and observe that since R2 and R3 are in parallel, the potential difference across R23 should be the same as that across each R2 and R3 considered alone. So what we'll do is find the potential difference across R23 first, and let us call it V23. That equals I1 into R23. That gives you 3.6 volts. And now we can assume the same potential difference exists across R2 as well, and therefore the current I2 in R2 equals V2 by R2, or 3.6 volts by 20 ohms. That gives 0.18 ampere. The third question is, what is the value of current I3? Well, we could solve this by using the same method as we did for the earlier question, or an easier way is to apply junction rule at point B, which means I1 is equal to I2 plus I3, or I3 is equal to I1 minus I2, which equals 0.3 ampere minus 0.18 ampere, which equals 0.12 ampere. So far we have dealt with circuits where current did not vary with time and was constant. But if you introduce a capacitor in a circuit, what you find is that the current starts varying with time. So let us study this variation in current, charge and voltage of a circuit that has a capacitor in it. So what we have here is a circuit that has a battery, a resistor and a capacitor that is initially uncharged, and we'll go ahead and close switch S so that charge and therefore the current starts flowing through the circuit, and as a result charge starts building up on the capacitor, and therefore a potential difference Vc equal to Q by C is created between the capacitor plates. And when this potential difference reaches the potential difference of the battery, that is EMF E, the current becomes 0. And since we know that for capacitors, Q equals CV, the final charge on the capacitor, that is when the capacitor is fully charged, should become C times the EMF, and let us say this is Q naught. So you see the charge starts flowing when you close a circuit, but the flow starts falling with time as the capacitor gets charged, because the positive charge that builds up here tends to repel more charge from coming onto the plate and completely stops the flow of the charge when it reaches the same charge as is present on the battery. And therefore you can say that during this time, that is time 0 to the time when the capacitor gets fully charged, the accumulation of charge Q, current and potential difference Vc across the plates is changing, and this is what we will try to understand with the help of an equation. So let us apply the loop rule to the circuit, and what we get when we move in the clockwise direction is EMF minus IR minus Q by C is equal to 0. And this term here is negative, since we know that this plate of the capacitor is positive and this one is negative, and therefore there is a drop in potential as we move across it. Now, you should avoid the temptation of solving this equation right away, since you have to remember that there are two variables in this equation, and these are I and Q. But fortunately, they are related by the equation I is equal to dq upon dt. So if we substitute this for I in this equation, what we get is this. And you must make note of the fact that the sign we have taken next to dq upon dt is positive, since the capacitor is gaining charge with time. So we'll make use of this fact later in the lesson when we understand the capacitor discharge. Well, to make sense of this equation, we need to find a solution to it, and the solution is this. And I've not done the mathematical derivation here, since you can find it in any standard textbook if you wish to see it. Well, what we should do is test this equation for its accuracy and also how well it allows us to understand the various parameters as the charging happens. So let us go ahead and put time t equal to 0 in this equation, and what we see is that this expression becomes 1, and therefore we get Q is equal to 0, which is true since at time t equal to 0 there is no charge on the capacitor plates. And as t increases to infinity, or say a long time later, this term becomes 0, and we get the value of charge on the plate as C times the EMF, which is again true since after a long time the capacitor gets fully charged, and at full charge the Q value is C times the battery EMF. So if we make a plot of charge buildup on the capacitor versus time using this equation, this is what the graph would look like. So you can see that at first the charge builds up very fast, but with time the buildup slows down, and this line becomes an asymptote to the curve. That is, the curve will touch this line only at infinity. Now if we take the derivative of this equation, that is find dq by dt, what we get is this expression. But then dq upon dt is nothing but the current in the circuit, so this actually shows how current varies with time. And if we plot this equation on a graph, this is what we will get. And you can see that at time t equal to 0, this part of the equation becomes unity, and initial value of the current is EMF by R, which we know is true. And if you take time equal to infinity or a very long time, the current falls to 0 as the capacitor builds up charge and keeps avoiding the flow of more charge till it becomes fully charged. We can also establish the time dependent equation for potential difference across the capacitor, that can be written as Vc is equal to Q by C. And if we take the value of Q from this equation, what we get is this. Again, we can test this equation for its correctness, and if we put t is equal to 0, what we find is that this becomes 1, and therefore Vc becomes 0, which of course is the case that is at time t equal to 0 with no charge on the plate, the capacitor has zero potential difference, and at time t equal to infinity or a long time later, this becomes 0 and Vc becomes equal to the EMF E, which again is true. Now, when dealing with RC circuits, we often use the term capacitive time constant, and the symbol used to represent it is tau and is nothing but the product RC that has dimensions of time. So the idea here is that if we wait for time t equal to tau and put t value as tau in this equation, the charge on the initially uncharged capacitor would have increased from 0 to 0.63 C times the EMF. Then it means that this is 63% of the full charge, or we can say that after time t equal to tau, the capacitor reaches 63% of the peak value. So if you're told that the tau value for an RC circuit is 2 microseconds and that of another RC circuit is 20 seconds, you can easily conclude that this RC circuit would charge up the capacitor a lot faster. So you see, RC value is a measure of how fast a capacitor charges. Well, let us see what will be the charge on the capacitor if we wait for, say, time t equal to 10 RC or 10 taus. So if you substitute time value as 10 RC, what you'll find is that the charge on the capacitor reaches 0.999955 of C times the EMF value, or almost 100%. But it never touches 100% because you see this horizontal line is an asymptote to this curve. So the curve never ever hits this line to reach 100% of the value, and that is the reason we say that it would take infinite time to hit 100% value. Now let us say the capacitor is fully charged to potential equal to EMF, and then at time t equal to 0 we activate a circuit like this with no battery in the circuit. In that case, you can see that the capacitor will get discharged over a period of time because the positive charge from this plate will move to the other plate, and with time they both will come to the same potential and the flow of charge will cease then. However, this flow of charge also constitutes current, and it lasts till both plates get neutralized. So once again, we are interested in knowing what will be the value of current in the circuit and the charge on the plate with time. So let us apply the loop rule again to the circuit, and we observe that the direction of the current will reverse, and the equation we'll get if we move in the clockwise direction is IR minus Q by C is equal to 0. We can then rewrite this equation as dQ upon dt times R minus Q by C is equal to 0. But then we must remember that the capacitor is getting discharged, and the rate of discharge should therefore be a negative term, and for this reason we put a negative sign here. So the solution to this differential equation would be this, and again I'm refraining from showing the derivation here that can be found in any textbook. So Q naught here is the charge when the capacitor is fully charged, or Q naught is equal to C times the EMF value of the battery. So we can see that Q decreases exponentially with time, and after time tau, that is the capacitive time constant and equal to RC, the capacitor charge has come down to Q naught e to the power minus 1. That is about 37% of the initial full charge Q naught. So a higher tau value would mean more time taken for discharge. Also, if we differentiate this equation, what we get is dQ upon dt, that is current I, that equals this expression. And this equation also tells us that current reduces exponentially with time, and if we do a quick check and put time t equal to 0, the current is maximum and equal to Q naught upon RC. Well, the minus sign that you see here is a mere indication that the charge on the capacitor is decreasing.